All right, here's section 10.4. So our learning targets for this section are first we're going to find probabilities of compound events, and then we're going to be using more than one probability rule to solve some real life problems. So first, what is a compound event? So these are some examples of compound events. So I'm looking at two different events happening. I've got A and then I have B, and those are two separate things. So if I'm looking at either of my two events, I have a union. So if I'm looking at either A or B, I have this union, which is kind of shown here. So everything is shaded because when I'm looking at either or, I can have it all shaded. So if I'm only considering the outcomes that are shared by both, so A and B, it's only this overlapping right here with this is called an intersection. And then I can also have a disjoint, right, where none of the events overlap. And so these are mutually exclusive. So you'll see down here these are mutually exclusive or disjointed. They don't share anything in common. They're completely separate events. So I like to think about, for over here, like if I flip a coin and roll a dice, those two don't have any shared events. So they're totally disjointed or exclusive, mutually exclusive of each other. Okay. So we're going to look at some overlapping and we're going to look at some unions here in these examples. So here's our first core concept. So the probability of compound events. So if A and B are any two events, it doesn't matter what kind of events, any two events, then the probability of A or B, that's the big word we're looking at here is or, is I take the probability of A and I add the probability of B, but then I have to subtract if there's any that are in the middle because I don't want to count them twice, right? Because these will be counted twice if there's some overlapping. So we see in our picture that these four dots, if I look at just A and I add to it just B, so I've got in A, I've got these 5, 6, 7, 8, 9, and in B I've got 4, 5, 6, 7, 8. So if I just add those, I end up with more dots than I have total because I have these ones being counted twice. So that's where I subtract this A and B. So I have to subtract any that are counted twice. So then if A and B are disjoint events, right, so if they don't have any overlapping, so then my probability of A or B is I just add my probabilities together. And I can do that because there's nothing overlapped, there's nothing that's being counted twice. So let's look at this example. So a card is randomly selected from a standard deck of 52 playing cards. What is the probability that it is a 10 or a face card? So here's that magical or, so we're going to be looking at probabilities. So first I want to think of, are these disjointed events or could there be some overlap? Well, I know that there are 10s in a deck and I know that there are face cards in a deck, but there are no 10s that are face cards, so I know I'm not going to have any overlap. So first I want to look at my events, right? So A is going to be selecting a 10. So here are my possibles. I can have the spades, I can have hearts, I can have diamonds, or I can have clubs. And then B is selecting my face card, so there's all of my possibilities there. So from my diagram, I see I have 4 possibilities for A, and I have 12 possibilities for B. So they're disjointed. There's nothing that's overlapped. I just add my probabilities together, and I substitute what I know. So I know 4 out of the 52 cards are 10s, 12 out of the 52 cards are face cards, and then I just add my fractions together. First thing I always double check is make sure that my denominators are the same, which they are here, so then I end up with 16 over 52. So then I can go ahead and simplify this fraction until I end up with 4/13. Then I can go ahead and divide that because we're using probability, we're talking probability, we want to look at decimals or percentages. So then I can use my calculator to find that the probability that I pick a 10 or a face card is almost 31%. So let's look at our next example. So a card is randomly selected from a standard deck of 52 playing cards. What's the probability that is a face card or a spade? Well, here I notice that I'm going to have some overlap because some face cards are spades. So let's go ahead and draw out what we're looking at. So A is going to be my face cards and B is going to be my spades. So you'll see here in my diagram that I have all of my face cards written in my A, and I have all of my spades in B, and I see that I have 3 that are in both, because 3 of my face cards are also spades. So I know I have to take the probability of A occurring, plus the probability of B, and then I subtract the probability of this stuff that's in the middle. So that's my general formula. So now I just substitute what I know. So I know that 12 of my cards are face cards. I know there are 13 spades, and I know that there are 3 that are overlapped in here. So I go ahead and write out my fractions, then I add them, and then again I simplify my fraction, and I use my calculator to come up with approximately 42.3% or 0.423% that I have a face card or a spade. So now just let's think about, does this make sense mathematically? Well, so if I look at all of my possibilities up here, right, I know that the spades make up 1/4 of the entire deck of cards because there are 4 different suits. So I know that the spades make up 1/4. But then I know I'm adding on more cards than that because I'm adding on the face cards of the other suits. So I know that this is actually pretty accurate if I just think about, did my numbers that I ended up with make sense? And here they do, because I know I need way more than 1/4 because I'm adding these other cards in. And this is more than 1/4, but less than half. So I know I did good. So we always want to just think about, mathematically, does my number make sense? So we talked a lot about this too when we're dealing with solving. Does a negative make sense in my answer? Well, if I'm looking for time, no, a negative answer doesn't make sense for time. So same thing here, we're just asking ourselves some quick questions of, does this even make sense? So now here's our next example. So out of 200 students in a senior class, 113 were either varsity athletes or on the honor roll, so one or the other. There are 74 seniors who are varsity athletes and 51 seniors who are on the honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? So let's look at our numbers and our values. So our event A is going to be a senior who is a varsity athlete, and B is going to be a senior on the honor roll, right? Because those are our 2 separate things. So from my information, I know the probability of A. So again, being that varsity athlete is 74 out of 200, because I'm told right here 74 of my seniors, 74 of my 200 seniors are varsity athletes. I know that the probability of B is 51 because there are 51 seniors on the honor roll. And then I know that the probability of A or B is that 113 divided by 200. So now I have to figure out the probability of both, of A and B. So I know that the probability of A or B is equal to the probability of A plus the probability of B minus the probability that they're both. So this is the same general formula that I've been using. I just know different pieces of it. So now let's plug in what we know. So I know that it's 113 over 200 equals 74 over 200 plus 51 over 200 minus this overlap. And we're trying to find the overlap here. So then I just kind of simplify and I solve. So I get all of everything to one side, and I'm left with probability of A plus and B on the other side. So then I just simplify my fractions. I go ahead and add or subtract. And then from here I can simplify further. So it'll be 3 over 50 or approximately 0.06. So I know that this is my probability, my 0.06, that a senior is on both the honor roll and a varsity athlete. So here I'm using my same general formula, I'm just plugging in different information. In the previous examples, I've known these 3 pieces over on the right side, and I've been solving for this A or B. But here I know this piece, but I'm not sure what the overlap is, so I can still solve and simplify for my overlap. From this, I can also answer if it asked how many students, right? It didn't ask me, because here I'm asked what's the probability. But what if it said how many students are both? I'm also given that information right here before I actually simplified, because I know there was 200 total students and 12 of them ended up being in both. So I can use this to find either the number of students or the probability. So here's your first monitoring progress. I want you to try this and see where you end up with. Go and try all 3 problems and see how you do. So here's our next example. So the American Diabetes Association estimates that 8.3% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that's 98% accurate for people who have the disease and 95% accurate for people who do not. The medical lab gives the test to a randomly selected person. What's the probability that the diagnosis is correct? So we're given a lot of information here, so first we kind of have to organize it. First, we want to figure out what our events are that we're looking at. So event A is going to be that the person has diabetes, and the event B is going to be that it was the correct diagnosis. So the probability of B depends on A. So these are dependent events, right? Because there's a difference on if they have it or if they don't. That accuracy changes, so it is a dependent event. So when A occurs, so when A happens, the probability of B is 0.98. So when A does not happen, the probability of B is 0.95. So I can just lay it out of what I know so far. So then we're going to go ahead and use a probability tree diagram. So the probabilities are given along my branches, can help us kind of figure out where we get some numbers. So I want to also use the complements. Now remember, a complement is where I take 1 and I subtract what I know to find the probability that it's not occurring, okay? So this symbol right here with the line, the dash over it, tells me that a person does not have diabetes, and the dash above B is the incorrect diagnosis. These are the complements of the probabilities that we have. So here's the big thing about using a probability tree. All probabilities for the branches must sum or add to 1. So if they go to the same branch, they must add to 1. Okay, so let's look here. The population of the United States is where we started. And I was told that we have a 0.917, that this person does not have diabetes, right? Because 8.3% do. So I can turn all of these into a decimal. So then I was told if the person does have diabetes, it was a 98% chance of a correct diagnosis, which means a 2% incorrect diagnosis. And then from down here, if the person does not have diabetes, it was a 95% for a correct diagnosis, and then 5 for an incorrect diagnosis. So to find the probability that the diagnosis is correct, I follow my branches leading to event B, that I have a correct diagnosis, right? So here we go. I've got some information here, and I'm going to use my tree diagram because I'm talking about a correct diagnosis. I'm not absolutely saying that they have to have diabetes and it's a correct diagnosis. I was really just looking for, if I give you the test, was I right? So now I'm going to be using my tree diagram. So I've got the probability of A, and I'm looking at my probability of my dependent events. That's where this is coming into play, right? Because B depends on A. So now I plug in the things that I know from my tree. So the probability of A is 0.8083, right? That's the probability that the person has diabetes. Then the probability that they got a correct diagnosis. And I add to that the probability that they don't have diabetes, but they also got a correct diagnosis. So I substitute the things that I know, and I go ahead and use my calculator, and I come up with my probability. So my probability that the diagnosis is correct is approximately 95.2%, or this 0.952. So now let's just think back. Does our answer make sense? Well, I know that the probability needs to be greater than 95% because 95% is the lowest here. And so I know that it's going to be closer to 95 because more people fall into this 95% category than the 98% category. So I know that originally before I start, my number is going to be between these two values, but closer to 95. So if I look back at the math that I did, I ended up pretty close to 95, so I know I'm right. So this is just taking the time to think through, does my answer make sense? And that's the question we always want to ask ourselves before we are just done with the problem. Does this make sense? Does this end up where I thought it was going to? So here's our monitoring progress. Try these and see how we do. See what you can come up with for them as well. So now let's look back at our learning targets. Our first learning target was to find probabilities of compound events, right? And that's what we did with this whole section, is finding those compound events. Do they overlap? Do they not overlap? What do we know about those things? Then we used our multiple probability rules, so several probability rules to solve those real-life problems. We also looked at, for the first time, a probability tree diagram, which we haven't really seen before. But these can also be used instead of our two-way tables or instead of some other ways, just to help us kind of organize our data and see what we're looking at in a way that we can follow it. So I was able to look at both of these learning targets, and I actually learned another thing too about using that probability tree. So now that we've done this, go ahead and work on your homework for 10.4.